Así que hola a todos, ¿cómo están? Bienvenidos los que están aquí presentes y los que están en línea. Vamos a ver quiénes tenemos en línea. I don't see the thing. I don't see the remote. I can see the participants. Where is it? Well, doesn't matter. Okay. So we will continue with.
Okay, you have a point.
With this thing. Yeah.
Okay, let's see.
Or do we have a laser?
Well, there's a laser.
I don't have it.
No.
Yeah. Okay.
Okay, let's try.
So
There is a pointer in the.
another layer of improvisation. So this is the second day of our practical mimic design course. Today we have the presence of our two teachers. From Finland, we have Dr. Mikko Varonen. We've been working together for quite a while. He's been co-advising thesis with Sepia. So, for example, Felipe Vargas is there. We've been working together, and also Wagner Ramirez was another one that Mikko co-advised. So we've been working together for quite a while, and it's been a real pleasure. So let's welcome Mikko. And our second teacher is, of course, Miguel Martínez, a postdoc at Sepia, and we've been working together also for several years, enjoying the fun of working together on several topics. A lot of fun. Yeah. So in this second day of the practical mimic design course, we went yesterday through the introduction and also through the instructions to get the AWR working, and now we will do the theory behind the microwave design that will lead us to design beautiful LNAs out of sweet transistor. That's it. So let me introduce you then to Dr. Mikko Varonen, and he will present us this lecture of mimic design from. Sorry. Yeah, from 5G frontends to cryogenic receivers for radio astronomy. Stage is yours, Mikko.
Thank you very much. It's really nice to be here. Rodrigo was saying we've been working a long time together, and I've been trying to get here for a long time, but now it's finally possible. So it's really fun to do this talk and together with Miguel this course of the LNA design. So this presentation is sort of a motivation for the generally on MMIC design, so integrated circuits. So we will go through some basics of technologies and then some examples that we've been working on at VTT. And VTT is Technical Research Center of Finland, where I'm working as a principal scientist in this MMIC design area. I also hold still Academy of Finland research fellowship post in the same area. So it's a five-year project with good funding, and we've been working with this funding. I've been working with Rodrigo's group, for example. So the outline of the presentation is here. I will briefly go through actually something about VTT because it might not ring a bell for you, and then we will go through introduction of MMICs in general, the technology, and then some design examples, which I guess I didn't notice that I would need to update the outline, but mainly those circuits that we've been working on, and then some kind of a summary after the presentation. So VTT is like it's a technical research institute which is between sort of university and the companies in Finland. So our role is sort of to make business out of the technology, but we also work on basic science too, but mainly we should also support Finnish industry and actually European industry maybe nowadays to leash the ideas and the technology to business for companies. There are some numbers there. One interesting is the net turnover. So 45% of actually the net turnover comes from abroad. So we are like doing international research for companies, and we have a lot of EU projects, that's European funding for these kind of things, and we have 2,000 employees. And VTT has a broad area of technology development or research. So here you can see some examples, one from biotechnology to quantum computers and chemistry, and many things which I don't even know all of them. Oh.
¿Usted inició sesiones de otro dispositivo? Ah, ¿de allá?
Technical issues. So you just press the blue button.
Accept.
Yeah, accept. Press in the back. Yeah, there you go. No? Minimize yellow one.
Which is minimize.
The yellow.
Yellow. Okay. Still the true. I will just move it away. Okay.
The yellow one. Yeah.
So, yeah.
Oh, now we are having there.
Good.
Now something there.
We're good.
Now. Okay. I found this kind of a slogan from our marketing material. So we solve the world's biggest challenges. Sounds good to me. And then, so I'm working in a team which is called Antennas and RF Technologies. And for that one, I also found a YouTube video. Let's not. So can we run it here?
Yeah.
You know how to run it.
Okay, you need to click on this.
Goes to the next slide. Should be there. Why you're not playing? I'm sorry, you need to escape the presentation. Escape the presentation.
Mostrarlo en el computador.
And is the video attached or is a link?
It's a link to YouTube.
Do you think we'll be able to?
Oh, there you go. It's now it's there. It's there.
Oh,
Habilitar contenido.
okay. Another technical. Hey,
Wait.
press stop. Okay.
So now we'll move the show again.
Right.
Who said they were
Yeah,
not?
I think so.
So,
Come
press play, and then let's do it from pin.
This requires reliable connectivity, new higher frequencies, and precise sensor systems. We at BTT have a unique team of extensive knowledge about millimeter wave technology, power solutions, and antennas for use in autonomous systems and robotics, wireless communications, public safety, and healthcare. Our work ranging from customers' early phase research and development to final product optimizations can be seen everywhere around us, from personal apps monitoring health, phones, cars, radars, drones, flight systems, and even space missions. Our world-class Millilab, a European Space Agency external laboratory on millimeter waves, contributes to the European space program and the competitiveness of the European space industry.
Okay, so that was our team short presentation, and we focus on RF and millimeter wave technologies. And in this presentation, I will especially focus on integrated circuit technologies for high frequencies. So when we talk about MMICs, we talk about microwave chips that operate, let's say, beyond 10 gigahertz up to terahertz frequencies. So some people talk about RFICs, so radio frequency integrated circuits. So I would say those are below 10 gigahertz. Now we talk about MMICs. They are sort of the same circuits, but maybe the design philosophy might be a bit different, so we can argue with the RFIC guys, something at least. And one question is, of course, that why do we want to go so high frequencies? So for telecommunication applications, we know that higher we go, sort of the wider bandwidth we have available. So we could send more data at high frequencies. For radars, it means that the radar spatial resolution improves in function of frequency. So antennas get smaller, which is sort of good, but sort of bad because of course the capture area becomes smaller. We will go through that one soon. Then there are scientific research like cosmic microwave background is measured at, I guess, at around 100 gigahertz. Or there's a water vapor resonance peak at 183 gigahertz, which can be used to measure the, I guess, the formation of clouds. Maybe Rodrigo knows better on that one. Then security screening or imaging can be done at, for example, 94 gigahertz. But there are several benefits to go there, but then there are challenges. One thing is, as you might know from the basic radio engineering, that the free space path loss is a function of frequency. So higher the frequency, sort of the loss is bigger. This is actually, I think, because of the antenna size becoming smaller. That is what radio engineers explain. There is no such thing actually, the free space path loss. It's because our capture size becomes smaller. That goes to details. Then, for example, it's hard to go through the wall if you want to send a millimeter wave signal. So that's sort of the benefit and the challenge. If you want to keep a secure connection with millimeter waves, it could be kept in the room quite easily because it cannot go out. But if you want to send out the signal, it's difficult. And then for the actual designers, usually the gain of the amplifier. So we want to amplify the signal. So higher you go frequency, the less you have gain on your devices, and less you have output power, and then the noise is decreasing your signal. It's making noise to the signal, so that becomes higher. But here we will go through that. We can go over these challenges too by clever design. So this was actually proposed by Miguel from his material. So to show that we have several technologies available for millimeter wave design. So we first of all have field effect transistors, which are can be made with different technologies. And on the right hand side, you can see the chemical options that you can do it. Then we have bipolar transistors, and depending on which applications you are going, you can basically select from this branch of trees. I hope I can make some examples. How can we, which ones should we use for which ones? And so here is a small explanation that which technologies you can roughly choose for what application. So traditional 3 to 5 technologies are the ones that done in indium phosphide or gallium arsenide. These are the high performance technologies. So if you want best amplifiers or highest power or lowest noise, you choose that technology. But the integration level of this one is really low. So then silicon technologies like the CMOS technologies, the one that you have in your mobile phones and in your laptops, that's sort of the mass production technology. So nowadays that can be also used for millimeter waves, but performance-wise, it's not as competitive as the 3 to 5 technologies. And then there's CG BiCMOS, which is sort of in between of the two technologies. Currently, on the left-hand side, you can see the indium phosphide traditional best technology that you can have, and you can design a 1 terahertz amplifier, so 1000 gigahertz. So that's pretty good. On the right-hand side is our work on CMOS technology, which is for the mass production. So there you can go barely to 300. So obviously, there is trades off between technologies. Maybe this one goes too much in details, but this basically tells you, if you want to later look into it, that which technologies are good for noise and so on. I will not go into details to that one. Then there are power amplifiers. That's the one that you want to use when you transmit the signals. So you need to have high power if you want to transmit. So there you have other options. Currently, there is a gallium nitride technology, which can be used, for example, 100 gigahertz, you can get a 2 watt output power easily. The right-hand side, that's the best power amplifier in silicon technology. So there we are well below 1 watt. So depending on your applications, you might select the other one, maybe for radars, the left-hand side, and maybe for some telecommunication application, the right-hand side. Or if you are clever enough, you use both of them. Here is also a comparison which you might want to see later if you are interested. And then I made this table, which could be used easily to select different technologies. So you can set the indium phosphide or the 3 to 5 ones here. They go higher in frequency, they are good in noise, but they're poor in integration. And then silicon technologies, they are poor in performance, but they are good in integration. So if you want to integrate a lot of functions, you select that. Or you mix up the technologies, which we hopefully will come soon. So now I will go through a few examples how we can utilize the technologies. So we've been working on E-band 5G development for backhauls. That backhaul is the link between, for example, two base stations. And this is now working at 71 to 86 gigahertz. So 10 times higher, several times higher than the current technologies are working. So now if we remember that, okay, the challenging to get a good link because of low power, poor noise, antenna size gets smaller. So now we can, let's utilize that feature that the antenna is smaller. So what we can do now is that we put several antennas and combine the power using the antennas. And if we add a certain type of phase shifter to each antenna, we can even steer the beam to different directions electronically. So now we need a clever phase shifter. We can do this operation and we can sum up all the power. So it means that for a receiver, if we have n times antennas, we will improve the signal and the noise ratio by 10 log n, 10 times. N to power 10. And in the transmitter, we will actually have a 20 log improvement because we both combine the power and we get a better gain from the antenna array. So here we have one phase shifter. So we have an LNA, then we have a phase shifter here, which controls the phase of the signal. And then we have a buffer. So on the right hand side, we can see that this is fully digitally controlled chip. So we can see that we can tune the phase 360 degrees, and we can also tune the amplitude. So we can steer the beam of each of the antenna to the same direction, and we can actually tune the antenna pattern of the whole array. And with this one, we can build an antenna array. So here we have 4 times 4 antennas. Each of them is one patch antenna here. And on the other side, we have a PCB where we have the phase shift. So one phase shifter is now driving 4 antennas. And here we can see that the red area is the main beam, and we control it with digital commands. Okay, so we need more antennas actually to make a good link. And it seems to be, now if you look at this one, it's not going to work if we want 1000 antennas, for example. So we need to now start raising the integration. Oh, by the way, so here we have chosen now the silicon CG technology because it's supposed to have high integration level and electrical controllability. So what do we do next? So we start integrating more stuff on a single chip. So here you can see the one unit antenna that was in the previous slide, so 16 antennas. So what we did next is that we designed a 16-element phase shifter chip which can drive each antenna separately. We place it on the other side of the PCB, and we can then use several of these chips to drive several antennas, all controlled by digital to analog converters. So here is one quadrant of this chip, which is 4 by 4 millimeter. So it has quite a lot of stuff here. Tomorrow we start designing one piece here, not with the same technology, but one element. But you can see that currently there's good technologies to have high integration level. And with this one, we can now tackle the challenge with the high free space path load or whatever. So we generate 128 elements. So we have 128 antennas here. So we can steer the beam and direct it to very narrow gain to get a long distance link between the receiver and the transmitter. And on the right hand side, you can see we can measure precise some of the angles. So what I'm talking about link distances now here. So if we would have a very small 2 times 2 antenna, we could send maybe a few centimeter link. Not very useful for telecommunications, what we are using now. but when we increase it, we start to get a longer and longer distance. So 1 kilometer with a QPSK modulation, this is 10 gigabytes per second, which we calculate. So looks like it's gonna work. The problem is with the DC power consumption, that's pretty high. So that's the next step to fix on these kind of chips, but looks good. Okay, there's another example. This is like as a radar perspective that you might remember that the radars are big and clumsy, which they are, but now with the MMIC technologies, we can make this kind of a small, very small radars. This is a MIMO radar where we designed our chipset. So we have 4 channels in a chip, or we can have 1 channel, and we can make it scalable as the previous telecommunication applications. What you can do with now, you remember that the radar resolution gets better when you go higher frequency. So this is a 60 gigahertz radar. So with this one, this has many applications. Here we can distinguish with this radar, we can distinguish several people in the room, and we can even measure their heartbeat or vital signs. We use it for drone detection. It can be used for micro movement accuracy below 700 meters, so you can measure something quite big. So there are quite nice things that you can figure out with this technology. And this was again with the silicon technology for mass production. Then if we go more traditional applications, so Rodrigo has been also working on 183 gigahertz water vapor resonance radiometers. So in an old way, it was done so that we use the best technology, the indium phosphide technology. So here's a figure of a NASA packaged one receiver. So they are using one separate high performance indium phosphide LNA, a second one a separate mixer chip, and then you have separate low frequency LNAs, which are not shown here. So our idea is here that we mix the technologies and take out of the benefits of each technology. So we still use the one best performing amplifier here, so that will define the performance for the receiver. But since if it's a good enough, you can add a sort of a bit worse performing chip after it, because this will define your performance, your noise figure. So why don't we use silicon chip where we can integrate all functions on single chip? And this would be then usable for small satellites or CubeSats or synthetic array radiometers for scalable ones. We can get a digital controllability, reduce the power, mass, and size. So here we have sort of mixture of the technologies, not just one. Okay. I will maybe talk something about that one later. So then we will now go to the other extreme, which is the cryogenic cooling, which is used for applications, for example, measuring the W band, the cosmic microwave background noise. So these are cooled receivers to 20 Kelvin, that's minus 250 Celsius. And the idea is that lower the temperature, the lower the noise, because we are measuring noise from the space. Our amplifier needs to have as low noise as possible. So we cool it down to detect that very weak signal. And this is the work that Rodrigo I was doing at the JPL and Caltech. So currently, these kind of MMIC-based receivers can have noise temperature at 100 gigahertz or performance at 100 gigahertz, which are better than the existing state-of-the-art superconductive insulator, superconductive based receivers. And the benefit of using our technology, the MMIC technology, is that you need only to cool 20 Kelvin. The superconductive stuff you need to cool 4 Kelvin. And that's a huge difference in cooling. Reliability is quite challenging for those ones. And we even get a better performance. So this is the work that Caltech guys did for Argus. In Green Bank Telescope, there's a radio meter. I guess they're having MMIC-based LNS. I guess this is the most sensitive one in the world.
For W.
For W1, yeah. Okay, so now our next idea is that, again, those ones are made with the idea of traditional, that we put all best technology and package it as a separate. So the work is similar as in here. You have separate chips and discrete functions everywhere, like a traditional designs. So what we want to do actually, let's use the same idea that let's take the best technology that defines the performance of the receiver. And hey, let's put silicon technology where we can again integrate more functions. So basically, we could scale up the whole thing. Now it was 16 elements. We could scale it up to 144 elements to make it 10 times better. So we were actually the first ones to prove that this is possible. So this was the first measurement showing that in this table that we can really do it. Okay, the performance is not as good as the best technology, but it's enough that we can put it after. And now we are working on a package for it as a single. We need to package it somehow for this. We are testing the single element. This is Miguel is working on this package. We hope to get it packaged soon. Waiting for a while to get it done, but that is what we are doing. And this is actually what Felipe is doing now, measuring today. I hope he's cool, or maybe tomorrow, Finnish times. So we really have the whole receiver separate. If this is going to work, then we can show that, change the strategy of designing these MMIC-based radio meters for radios. There was one thing about packaging. Okay, so basically with the PCB technologies nowadays, you can go up to 140 gigahertz maybe. But then you need to start figuring out also how you package these chips if you want to make a sort of, for commercial applications, something useful. I mean, these ones are okay for, for dedicated high performance. You need high performance and you want the receiver to work for one, you send one Earth remote sensing satellite receiver, and that's enough. You can work with this kind of a packaging. But if you want to work for consumer applications, then the packaging also becomes critical. So this is what we are working now at VTT, is that we actually produce wafers, of silicon wafers, where we could package the MMICs like in a production, that we just clamp these chips there and we get a full wafer of, for example, a radio for imaging or something like that, or telecommunications. So that actually comes to my summary, which was clever, because for some time there's a good opportunity with the MMIC technologies to design new applications. You can even figure out new circuit architecture because you have so many technologies to choose. But it's not the MMICs, it's the whole system. So you can work from component level, from the device level to system level. You can work on electromagnetics for packaging the MMICs, the digital design. You can do on-chip antennas or PCP antennas with the MMICs. And you can do cryogenic cooled receiver for 6G telecommunications in this area. So that actually concludes my talk.
Very good.
Any questions?
Question. Maybe if there are questions, you can hear me.
Are you doing something for the LEO satellites? K-band,
Satellites.
like
Not our team, I think. Yeah. There was a call, European Space Agency, but I guess we lost it on that area. It wasn't. I'm not sure if it's LEO satellites.
That's some question I gave no comment. No. Very good. So
I have another question. What is the, I don't know how to put it, when you the interface between the two different materials, what is the main problems that can come from that?
I guess Miguel would be a good answer here. For example, if we combine indium phosphide LNA with a silicon LNA, so the main challenge there is to get the signal from this chip to the other chip. So Miguel has been now working on flip chip technology so that we can get the signal to the silicon chip. So I don't know if it's
Yeah,
yeah, but that's a challenge.
The main point is that different technologies have different clamping points, as we are saying. So, for example, silicon has the connection on the bottom. So you need to put the things inside, just solder it, I would say, on the board, like in a PCB, but it's not exactly a PCB. But in the case of the indium phosphide, you use wire cool things that allow you. And the point is, we are really here, and you will see about the matching one to the other. And even those small cables that are really tiny ones impact a lot on the performance of this match. So in order to make it a test and also mass production, it's really this is still on business. It's still on a work in progress.
Okay. So that's what you mean by integration performance.
In the summary, or yeah.
In a table with the FAPI and subphase.
Okay. That is a bit different table. The integration means the integration level on chip. Where is the table? This one, yeah.
How much functionality?
Yeah, how many functions you can put on a single
Okay.
chip. So CMOS is like in the computers, you can put everything. But the high performance ones, you might do one amplifier, like 3 transistors. Here you have millions of transistors. So that is this integration.
Thank you.
So, thanks very much. One question about, so what are the requirements for the backbones on 5G and 6G? And, so for example, do they need to work cryogenically in order to, no?
No,
That's probably just a lot of power. I think they need to set out a lot of power. That's the main thing.
yeah, I mean, we use antenna arrays to get the gain.
Directivity.
Yes, directivity with several antennas. And that should be also steerable.
So phased array.
Phased array.
Phased array. Yeah, but they're not cool.
No, the problem is to get them cool enough to get the heat out. So that we consume so much power in a small area. But that's the challenge for,
So they don't burn.
yeah.
They burn. And what are the limits of telecommunication right now? For example, BBB, what's the highest frequency they are working to transmit?
So we are
Data.
working on D-band, that's 140, 150 gigahertz.
Bandwidths are huge.
Yeah, they are, I guess, tens of gigahertz. Well, they are divided. There's no yet any protocols or anything like that for D-band. So, but the bandwidths are large, of course.
Right.
Question, but I'm not really sure how to ask this. So let's say, so, if you have this chip that is coupled to the silicon chip and the don't remember the name,
Indium phosphide, for example. Indium.
You have two materials, but how do you know how the temperature influence in like signal and both are influence of the of the data.
So for both technology, if you cool them down, the noise performance gets better.
But my question is referred to the two different elements of the chip.
Mhm.
So how you can make a comparison about on the first part for the Windows, the second part for the silicon, and how you can observe, for example, that one part is working efficiently and the other.
Once you have packaged it,
Yes.
for example. Okay, one option is that you first measure them on wafer and then package. But for silicon technologies, the yield is usually so good that you don't need to even measure. But that's sort of a discussion currently. For example, the chips that I'm presenting, you cannot, there's no way you can measure this. So they just need to be packaged. So one thing is that we make on-chip testing system. So we make sensors to figure it out if it's working. So then we could turn off the non-working and tune the gain of the array with digital commands to fix it. But it's still sort of, you have 126 elements, almost all of them are working. I don't think you need to do it, but that's, some chips have it already. They really test on the fly. We are partly doing it, but not completely. We have a power sensor. That's a good question. It's not. That's not easy.
More questions? Yes, next one. All right, thanks very much. Thank you very much. Yeah, yes, good. Now, let's turn the microphone to Miguel.
The Mikko one was the funny presentation. My
Wow,
presentation is not funny.
No.
Yeah, this is the not funny one.
You're not advertising yourself very well.
I only say so they get reality. So the idea is not to make a presentation of everything in the sense of it's not a class. The idea is to let you know some basics so you can know more or less what is going on. And later on, okay, you have some questions and so on. But the idea is that Mikko will do the practical part. Here in this presentation, there are a lot of formulas, there are a lot of theoretical basis that we are not going into because you're going to see the funny part, the really practical part of how to mount a real device. Well, Mikko will take care of that. So the idea is mainly to get the basic background of it, and so let's go. First of all, we are going to see some of the what it's most care of, or we care most is the saver part, because we are working mainly in astronomic instrumentation together. And this is mainly related to noise and gain, and it's related also to the previous question that we were doing. Later on, we will discuss a little of transistor technologies, common metrics of LNAs and so on. What we mean when we say that we want to match an impedance of the LNA or something like that, and what we get from it. And finally, what is the Smith chart, and in fact, what are you going to use in fact in the AWR software and so on. So first of all, talking about noise, there are many different kinds of noise that you can find in a circuit, and it depends mainly on the kind of device you are using. But the most important, I will say, is the thermal noise, and it's mainly occurring in all devices, and it depends on the temperature. So if you have a resistor and it is, I would say, in a or embedded in an environment at a particular temperature, it has a movement of the electrons, and the electrons itself will provide it a noise, right? Will generate an average noise, RMS value that will behave in voltage following more or less this formula. That is 4K, that is the constant. T is the temperature in Kelvin, B is the bandwidth we are measuring, and R is the value of the resistor itself. So if we match this resistor with another resistor, providing the maximum transfer, so we will get a power of the output that will be directly dependent on the temperature and the bandwidth. And this is why we usually call a device that has an equivalent noise temperature, whatever is the kind of, I would say that it's a white noise, because it spreads the noise equally in all the different values. But we say that it has a particular equivalent temperature, but it's related directly to the noise power that we are getting from this device, whatever it is. So each time we are talking about noise temperature, we are discussing about a source that provides white noise. So spreads equally in all the different frequencies, and it's directly related to its power. So the idea is that we can do exactly the same with an amplifier that is noisy, and we can say that it's really an ideal amplifier without noise, but at the output it behaves with an equivalent temperature, but at the output will be also amplified. So in general, all the different LNAs or amplifiers that we're going to work with, they will behave following this formulation, in which we have the gain on the amplifier, the Boltzmann constant is the TB, the equivalent circuit noise, and the band. So this is the most common formula that we will get.
We can talk about equivalent temperatures or noise factor that are the same. It's a different way of representing it. And the noise factor itself is simply a ratio in between the signal to noise ratio of the input related to the output. So if we spread the formula, we finally get the relationship in between the noise factor and the equivalent noise temperature. And it's related to a reference temperature, T sub 0, that is commonly used or commonly reference to 290 degrees Kelvin. Sorry about that. So this is the most common formulation, the way of making the calculation back. And when we discuss the noise figure, is exactly the same as the noise factor, but in dB, so in decibels. So it's exactly the same. Also, the different LNAs that we are going to buy or fabricate, they are expressed in noise figure or noise factor. So what we get, in fact, from an antenna, we are working with astronomical receivers, is a signal from source. Also, we have a noise from the sky, from different kind of sources and so on, but also we have a black box that is our receiver. And this receiver itself has its noise. And what it's commonly known as the radiometric equation is a way of calculating which is the average fluctuation that we will get at the output of the receiver. And it's mainly dependent on the system noise temperature, which is in fact the temperature at the input of the antenna plus the temperature of the receiver itself. So it's noise. Divided by the square root of the bandwidth of the receiver and the integration time in which we are integrating or averaging the signal. So what we are going to want is minimizing this value, the receiver noise, because it will provide us the less noise, because this other noise will be only affected at the antenna by the gain of the antenna itself. So whatever is this black box, it's composed by many different elements in cascade. So we have the penguin, we have many animals, but each of them, they have a gain and they have their own equivalent temperature. So if we cascade them, sorry about that. If we cascade them, we have, in fact, the gain at the output will be, in fact, the multiplication of the different terms of them. So it's amplified here, amplified here, amplified here, and here. So we have the total gain. But the final or the output noise temperature of the system itself is calculated by the freeze formula. So what we're going to have is that the total noise temperature is mainly the first one plus second divided by the gain of the first amplifier plus and divided by the different gains. So what we see here is that the gain of the first amplifier rules the most. So we want a large gain, but also we want a very small noise temperature at the first in order to make it a total noise temperature or noise figure, the lower ones, in order to minimize, which is all system.
Can I have a comment?
Yep.
So this formula was the reason that we can mix the different technologies in the radio. So we take the test element from the indium phosphide. If it has enough gain, the G1, if that is high enough, the P2 doesn't matter. So it can be the not so good amplifier. But we can integrate using that one. A lot of stuff on signal. This is needed.
I think that this also answers the question that we already have. So in fact, what we are having in the front end of our receiver itself at the beginning of it, if it's possible, we want a low noise amplifier, and this is also why we are discussing about millimeter waves or microwave low noise amplifiers in this. What we want is an LNA at the front, which has very low equivalent temperature, noise temperature, and try to have a very high gain. But in fact, it's a trade-off. We are not able to get the best of those all the time. And this one will be the one that will rule and provide us mainly the minimum detectable signal that will be the signal which will be the minimum above the noise. Okay, and this is what, in fact, as many of you have been already seeing, what we know as a super heterodyne receiver that provides us the ability to select in between the different frequencies at the input. But in fact, the reality is that only one amplifier is not enough. Usually we need to amplify a lot. So what we should do? We should put, of course, a very good LNA at the beginning and also a very good second one. And depending on which one is cascaded first, we will get two different values. Even if those are really good, it may not be the best one. So the selection of the best is the one that provides what is known as the noise measure, or is M factor, and this is in fact the value that you have to select the lower in order to get the better response or the lowest noise temperature. So a lot of formulas you have seen, but the idea is it's a very quickly seeing which is the most relevant part of all of them. So as we have already seen in the presentation, so the LNAs are made of transistors, and transistors are made of different components, mainly in the they are of groups 3 to 5, and they have many different properties, and depending on which you select, then you have different electromobility, hole mobility, saturation, a lot of physical parts that we are not going to see into detail, but they behave differently. That is in fact what we see. And when we are into the millimeter wave world, in fact, as Mikko showed in his presentation, we have different kind of transistor technologies. In fact, those that became from the FET kind of devices, the ones used for the millimeter wave technologies are the HEMTs, the high electromobility transistors. Those that came from the bipolar transistors are the HBTs, the heterogeneous bipolar transistors, as the hybrid technologies in between those are the BCMOS technology that, as Mikko already presented, provide the best in terms of the cost reduction and larger integration. Okay. But when we are discussing different kind of technology in terms of the transistors itself, one of the most relevant parameters is for millimeter wave operation is the transitional frequency that is commonly provided by the manufacturer, and is the frequency at which the ratio in between the input and output current gains becomes 1, meaning that there is no amplification of the current on the transistor itself. It can be also calculated clearly using another formula, but the idea is that this is also related to the maximum oscillation frequency. That is what we care the most, which is the frequency at which we are not further having more gain. So the input power, the output power equals the input power, meaning that we are not amplifying anything. And then those two frequencies are related using this formula. And as we see, it's commonly this maximum oscillation frequency larger than the FT, and when we have a technology that is known as balanced, that means it's well known, it's typically around this value, 1 against the other. So in millimeter wave, we are using technologies that used to reach for transitional frequency at least 300, and as Mikko already discussed, nowadays indium phosphide HEMTs are the ones that provide the best performance in terms of low noise and maximum gain, and they reach transitional frequency and operational frequency up to 1.5 gigahertz, so 700 gigahertz and 1.5 gigahertz. And a lot of information here, but as you can see, in fact, this is much similar to what the people are really presented. So we are not going to the integrated. In general, we are talking about LNAs, and they are made of transistors. But how they are built inside? The idea is that the transistor, which can be of different kind of technology that we have seen, first of all, is biased. What means biased? It means that a DC current must go through it in order to provide a operating bias, operating operation to determine which is the operation point. And this impacts a lot, in fact, in the noise figure or in the noise temperature that we will gonna get. Later, we have an input and output matching that will be seeing how to develop or design them. In some cases, we have also feedback that improves its behavior, and also source degeneration that is typically made by the addition of an inductor to the ground. This kind of configuration is typically the most used or most commonly implemented, but there are other ones. This is the common sort that we have really seen, but okay, this is the one degenerated. This is the common gate or common base, depending on which is the transistor technology, and also the cascode. Each of them provide different characteristics. Mainly, these common source provided the lowest noise. So for the implementation of low noise amplifiers, we are going mainly to work with those. But cascode ones provide not that bad noise figure, but much higher gains. Okay. Next thing. Which are the most common metrics when we are talking about elements? So the first and most, I would say, generic one is talking about the bandwidth. Bandwidth is only indicating which is the point at which the gain is decayed by 3 dB, which means mainly that the gain is divided by half. And it provides us a space of frequencies in which we are going to operate. And it's divided by the lowest frequency and the upper frequency, and those are the typical formulas in order to calculate which is the bandwidth, and also depending on the quality factor of cool factor. Okay, another thing that is really relevant in LNA is the power that it consumes in DC, but also which is the ratio in between the output power versus this power consumed in DC, and it's known as the drain efficiency. We have also to take into account that in order to power this amplifier, also some part of the input power is also consumed. So in fact, there is a metric that is the power added efficiency that takes into account also the input power lost in order to make it work, let's say. And the total efficiency is another way also to calculate this kind of loss of the input. So as you have seen, or you're seeing, in fact, there are a lot of formulas. The idea is to bring it to you. So if you need to use them in the future, then you have to. This is a really relevant metric of an LNA, and it's the 1 dB compression point. What means? Means that the amplifier has you expect to have a linear response, but it reaches a maximum in which it saturates or reaches the compression level. And we measure this non-linearity as the point in which it deviates from the linear curve by 1 dB. We measure it like the input power at which it changes or deviates, or the output corresponding to it. This is the input power, and this is the output power. And this is the formulation that we can use in order to get one from here. And this, in fact, provides us which is the linear diameter range of the entire amplifier. So from the noise level to the maximum point of linearity, we have this LDR as the operating linearly area of the amplifier itself. But again, taking into account the non-linearities, when we have a non-linearity in a device, we can model it using the Taylor expansion. So in fact, if we model the Taylor expansion of a single frequency signal, we will see that in fact it generates, as you see, a square, a cube, and so on. And finally, what we get is a bunch of terms that increase in frequency. But in some cases, those non-linearities or harmonic distortion that is known are into the frequency band of the LNA. So in fact, what we want is to minimize those. This is the total harmonic distortion formulation that in order to calculate it, or that many providers can bring it to you. But what happens when we have several, or at least two different frequencies at the input, is that they mix in between them. They have what is known as intermodulation. They behave like a mixer, in fact. So what we have is a bunch of terms, but that depend on differences of the different frequencies, and different terms that are twice the input signal, or twice the first signal, minus the second one, and so on. And then what we have is second order harmonics that are made those plus and minus of the first and second, and third order harmonics that are in fact those with one that generate this m plus n equals 3. And these third order are really relevant because they are in many cases into the band of the amplifier. So this will generate large noise errors that are in fact not noise, are intermodulation distortions that generate signals into the band, and we can measure it using this formula that simply relates the output power at those frequencies that are not desired to the ones that we want in the band. And this, in fact, also generates another intercept point in which the linear curve of the amplifier plus the linear curve of the third order intermodulation interconnect generates a point in which we can define which is in fact the spurious tree dynamic range, that is the range in which we are not having or we are having linearity, but we don't have those spurious or those intermodulation rates. So if we have an amplifier, we would like to work mainly in this range, the SFDR, but not in the LDR, because if we are working in this other range, we may have those undecited frequency ones. Okay, a lot of information. I don't know if there is any question by now. It's like a train, no? So you are going like, and you provide a lot of information. So yeah, now you know. Amigo will explain the order. So the main idea is that now you hear all that. Now you will see in the computer most of those parameters if you wish, and you will really know if they behave correctly or not, depending on those parameters. And this is the part in which particularly Mikko will work the most. This is the integral mapping. Later we will explain what is the Smith chart, that is a graphical part, which we will also see in the software program. So let's go on then. Okay. Okay, it's a good question indeed. So for those who didn't hear it, how the ripple, that the ripple is this deviation from the linearity of the bandwidth in the operating bandwidth, I would say.
This, in fact, I cannot say that it's a non-linearity because it is, in fact, a different.
Into each of them, we have a linear behavior, but what we are having here is a different class mix and amplitude. So what we are seeing, in fact, is some of those frequencies will be a little higher than the output power. We can calibrate it in post-process, and the final design, I will say, we do it with the whole. We don't like large ripples, but you have to consider that it will depend on the kind of filter that you are developing. For example, Cryogenic filters are the most, I would say, restrictive one, providing the most large decay, depending on the order of the filter, and they provide a large ripple. But if you have kind of the filter that is known as the bubble wall, is the smoke. It won't impact the final working much because we are not below the 3 dB point, which defines which is for band. The ripple is always lower. Okay? So it's only a matter of calibration of the time. I don't know if you also want.
Not much really. I don't think there's much to do with the ripple. The ripple, it's the deviation from the flat bandpass response filter. It's not to do with the linearity. There's no non-linearity there. But yeah, sometimes you see ripple with the response of interconnections of components due to standing wave. And they look pretty much like the ripple that you have there. And in such cases, if you have a spectrometer that you're using to detect the signal, you will just measure the bandpass with a terminated input, for example, and then remove it, because you always have this behavior there. So there are techniques to take it out and end up using the whole bandpass anyway.
What Rodrigo just said now is in fact one relevant part of matching that we are going to see now. In some cases, we are seeing something like a ripple, but it's because not of the behavior of the system itself, because of the non-well adapted resistances. It won't be resistances, it will be impedances at the output or the input of the system. So what in fact Rodrigo said is quite good, in the sense that we need to do a good matching in order to minimize what seems to be a ripple, but it's not. Exactly what is known as standing wave. So, in order to continue with the machine that we were going on, this is in fact something related to these standing waves. In fact, it's the basis of it. So what are the is parameters that most of you have maybe here, and it's one of the bases of microwave engineering? Whatever is a system, and independent of the number of input that it has, we might define it with a characteristic impedance, theta 0. Okay, this is, I would say, the most standard way of doing it. At the input of each of those ports, we can enter a signal, but if it's not well matched, if the impedance is not well matched there, one part of the signal won't go outside to the output load that we have and will be reflected back. This reflection can be measured directly using these S parameters. But if each of those is the S of IG means the parameter S at a particular output depending on the input. As we can see here, is the input signal is G, and the output signal is I. This is the minus signal indicates that is the reflected one, plus indicates that is the incoming one, and it's mainly a ratio of them, considering that any other port is not transmitting anything. So the main idea is to see at each of those ports which is the reflection term that goes back when we introduce something. This is what really measures a DNA, a vector network analysis. And the idea is that they provide this kind of scattering matrix with all those terms, and it's quite useful because it's, I would say, it's the key for what we are going to do. It's a way of explaining which is the impedance of the system itself, whatever is the system and whatever is the number of input and output points. So imagine that you have what we call a two-port network, that is whatever is the device, that is, I would say, indicated or displayed by its characteristic impedance, zeta zero, and this matrix that we have already known, it's always connected to an input and output load. And this defines those two connections, reflection coefficients at the output and at the input. Well, this is the input and this is the output impact. That measure which is the amount of reflection that we are going to get. This is the amount of signal that is going back to the user. So it is not well adapted to the memory. And this is seen directly on those loads that are the input and the output, but we can do exactly the same, but seen on the system itself. So we see the reflection coefficients to the loads, and we see the reflection coefficient also pointing towards the system that we are taking into account, and this depends mainly on the S parameters that we have already discussed. So we have two different ways of seeing a same port, but it depends on the point of view which you are seeing it. And this, in fact, depending on this kind of connection, provide us an input power that is going into the system or the transmission system that can be or cannot be the maximum power, which is this one, PAVS, in which the reflections are matched, meaning that we have a well match in the output or input in this case, input loads. Exactly the same for the output load and the same on the power available at the network or the source. This is simply what they are called. What this means, in fact, is that we have different ways of measuring the power gain of an amplifier. We have a power gain that is simply the power at the output load versus the input power that we put into it. So this is the formula. If you need to use it, simply use it. The variable power gain that considers that both are well matched. And the transducer power gain that is in fact the most used one because it takes into account all the different parameters of the non or possible mismatches that could be in the network or in the input and output system. So those this transducer power gain, you only have to take into account the formula, and that is also can be considered using an approximation. What means is that if we consider that the signal never will come from the output to the input, then S12 equals 0. So signals are going always in this direction and they are going amplified. But not on the other side. Then we can simplify things, and in fact what we can do is multiply these through 3 terms, and then this is in fact the formula that you need to use. This is a simplification that provides us a much easier way of working with them, and the maximum the unilateral power gain that we can get is in fact this one. That this is also another formula that you will use in case you need it. As we have seen, in fact, everything will depend on the input and output matching. So we will get different power gains depending on the matching that we get at the input and output. And we can separate the things in this way. So we are going to work with Mikko in the matching of the input in order to improve it as much as possible, and also the matching of the output in order to get the maximum power of it. But not always we are going to have maximum power, because this matching also affects the noise. And what this means is that there is always a behavior of the noise that depends on the matching, that behaves like hyperbole, in which there is a minimum, but this minimum don't have to be the same as the maximum gain of the matching. So we will have a trade-off in between, which is the gain that we get, in order to lower our going on. Because in some cases, or in most of the cases, when we increase maximum the gain, we are also increasing the. Those are the formulas that are typically used for this noise figure, depending on the matching. But those are the typical values that we can find in providers that they will sell us LNAs, so they provide these different values, and this in fact is the formula that you will need to use in this case. Also, what will happen if we have a very good amplifier that has a huge gain, but some of the signal gets reflected at the input of the signal. So what we will get is an instability, because it will amplify it, amplify again, so it will behave totally unstable. So it will generate a tone particularly, or even it can burn itself. And this is known as the stability of the amplifier itself. And it depends on the reflection coefficient at the input and at the output, because also at the output can happen exactly the same. So the thing is that it may start oscillating if the impedance, in the sense of what we call this matching, they have a negative value. And we have two different kinds of stabilities in an amplifier. That is the unconditionally stable, meaning you cannot never behave like that, meaning it works well. This is what we would like always to happen. That is never, never, ever, ever, we will have this situation in which it will behave unstable. And then we will have amplifiers that will be conditionally stable. In some cases, they may have this behavior and they may fail. So we have to work with them and have a matching that avoids this behavior. Those are the particular conditions of the stability. And in fact, there are three different tests that can be used for measuring it. Or measuring. The first one is that it's conditionally stable if at a particular frequency we ensure that the input and output are smaller than 1, reflection coefficient. The Rayleigh condition in which the K is larger than 1 and the absolute value delta is smaller than 1, and also the mu test in which this mu is larger than 1. So those are formulas that you will use in case you need them, but the idea is that those three conditions will allow you to verify if the system or the amplifier behaves stable or not. And then what we are going to use in most of the cases, in particular with MicroPad, is Smith chart. That is a graphical tool in order to verify the things that we have already discussed. In particular, the Smith chart, what it is simply a transformation in between the impedances and the reflection coefficient. We will consider, in any case, a normalized impedance. So we will have zeta divided by zeta 0, means typically zeta 0 equal to 50 ohm, but it will depend on the kind of application that you have. And in this case, if we have an impedance that is 50 ohm, then we will consider it 1. And this is the relationship in between the reflection coefficient and the normalized impedance. and it's turned back, so we can measure one or the other. And in fact, this defines a real and an imaginary parts. And those are defined by two different kinds of curves. One of them is circles that have a center that is mainly dependent on the real part, and those curves that are mainly dependent on the imaginary parts. And this is only for seeing where is located everything. This is kind of a strange, I would say, plot in which the center is this one, that is the 1, 0. This is in fact the theta equals theta 0. If we consider 50 ohm, then it will be 50 ohm. This is the infinite real value, and this is the zero real value, but we can have also positive and negative imaginary value. So we can plot any kind of impedance in this kind of plot or system. So imagine that we have here in particular a point, and we want to know exactly what it is you can see here 0.4 in the real part, so 0.4, and in the imaginary part you can see that this is 0.3, and this in fact means 0.4 times theta 0 minus, because this is in the negative part, 0.3 times theta 0. Okay, so each time we see this, we can relate either one value, but also one reflection coefficient. Okay, that Mikko will explain later. But what is the good part of the Smith chart? The good part of the Smith chart is that it provides us a very useful tool for representing what we know as the circles of continuous power gain and continuous noise period. So we can represent a circle in which the center at the input or the output is this value, and the radius is this other formula. For the gain, for a particular gain that we want to get, but also for the noise. So we have the center and the radius itself. Those are formulas. You can use it when you want, but the thing is that you will be able then to graphically design the matching in order to get which is the maximum or minimum noise and maximum gain that you could get on an amplifier, and even get which is the stable circles, stability circles all together in order to design it graphically only once. So again, we have circles with the center and radius defined by those formulas. And depending on the S parameters of the input or the output, depending if you're matching the input or the output, you will get circles that indicate in gray, which is the stable part in which you want to do this matching. When you want to put the gain and also the noise all together, as you see here, this is the unstable region. You want to be outside of this one in order to behave correctly. So in fact, graphically, you could have a tool in which you can clearly do the design of the entire system. And nice. It has been a really large one, but you made it. Thank you. I don't know if there are any questions. I hope not. Okay, Mikko will explain the funny part. This was as I told you, this is not the good part, it's the bad part. But now you know. You will see this graphically on the software. You can share the yes, it's already on the Google Drive. The idea is that you have these formulas anytime you want, and also there is a document written in which there are all the different references that you can go through. Yeah, maybe. I need to load this other one.
I have a question, but it's not
Okay, go ahead.
it's more. What do you think about Moore's law? It has a limit in the maximum, no, in the minimum size of the transistor. What do you think?
I think this is a more question for Mikko, but the Moore law is for the speed of the transistor in digital world. We are dealing here in application of analog signal, but nevertheless, Mikko, what is the one?
It's I think the CMOS foundries now are having like it would be a 12 nanometer technology. So it means that I think it's more of doubling the transistor count. Isn't it that the most
It's integration.
integration level?
Per unit
The
area,
amount of
Yeah,
transistor
you double
anyway.
over.
number of transistors per unit
So
area.
now they are running CMOS technology. 12 nanometer. But that starts to be the limit of that. Because you cannot squeeze it anymore. You don't have any more atoms.
To get the gate into it.
So in that sense, the Moore's law might end on traditional.
But they were dealing
Then you, yeah, then you
3D,
figure out something else. So maybe it's not.
3D integration.
but they were also related to the maximum frequency that they could reach because
That
that way
will affect the speed of the transistor to scale it smaller and smaller.
but this is mainly for digital. I don't know if there is any kind of law also in the world.
Well, I mean, we can faster transistor the scale for digital purposes too. It affects millimeter wave design too. I think
That is a very good
the max
question.
goes higher.
As we saw here, okay, a lot of things. The size of the transistor itself defines the capacitances that they are embedded into it, and this has a real direct impact on which is the maximum frequency range at which it can reach.
We are actually for amplifier design, we are more interested in the max, the next.
It's
Well,
also
that's FT is in there. So this is the maximum frequency of oscillation. So that's the highest frequency you can design an oscillator, or that's when it's zero. Just below that one you can design an oscillator, but it means that you basically also can design an amplifier. Because you can make that oscillator that you have to yeah. So F max typically goes and FT higher when you scale down. So it helps our work.
but they okay.
They don't care about it, but we get it free.
Some trends related to Moore's law for RF that was showing different technologies and showing how Max was changing with time.
Ah, okay, that much is.
That's very interesting. Yeah, for
That
different
follow.
technologies.
Might follow that.
I think some of them, like the ones that are recently being explored, like silicon germanium, they have a vertical increase in max with time. Then other ones, maybe indium phosphide or phosphide,
Which is
yeah, but it's the increase over time. But of course, indium phosphide has the highest maximum frequency of oscillation compared to the other technology, but it was the changing.
So there is
all for error.
there is a kind of
Things that you see on the microwave magazine. Entertaining things. Good.
well,
Do we have questions over?
I don't know.
No, I see there's not. Any other questions?
For Mikko. And they're asking about the strategy. They say something about the protocol. You don't say you don't have the protocol to use the technology. But how you build the technology like this? So feedback there is still not, how do you call it? It's not standardized for high frequencies or up to 50 gigahertz. So, but the idea is that also the companies like Nokia and Huawei, they are affecting the standardization. So what they want to do is that they want to build their demonstrators and to publish and show them, okay, we should follow this. But they want, yeah. I don't know if that answered your question, but
So because when I read about the 5D, they use the protocol 800 on something like that. Under the
That's a standard, the IEEE standard.
for maybe for low frequencies.
Low frequency.
So there is like, okay, maybe D band is not 5G, it's already 6G. So we're talking about sort of 6G. And so I guess it's at 28 gigahertz now that you really have the devices running.
And the other question is about the implementation of the 5G and the phase array. Because you see the problem, right? What is the EFCF signal you measure in time digital part? Because you have mixers and you obtain an EF signal. What's the bandwidth of
The IFC bandwidth. I don't remember. We actually have modems for that.
But are they connected to high-speed digitizing?
Yeah, we have modems coming from real modems that we are using to test, but I don't remember anything about this. Actually, yeah, I'm not doing the tests, so.
That box there is the one that is called Lenny. Yeah. That box. So, 5 gigasamples per second. And that is was connected by on informing mode. That was one. There are 2 digitizers there. There's the 5 GSPS and also the 16 inch with 256 megahertz low frequency phase array. That is working in that platform. That's the guy. The phase array guy. What's that?
But I think that they survived the course, no? So at least first and a half. Because Rodrigo already presented an introductory part of it. So tomorrow it will be fun. With it.
So I uploaded to the Google Drive the paper with the transistor model that Mikko did tomorrow. We have to try and turn that transistor model into an AWR encapsulated box. We'll see how that goes. We'll try. And all the presentations are in that Google Drive as well. So you can open them up. I see that you have access to it. Yes. So everything's clear. So tomorrow at 3 p.m. I think Mikko will start with the introduction of the design technique and the design environment, and then we'll go into the practical session. Then we'll try to design.
The fun part.
The fun.
The thing is, I will be using ADS. So
we will need a translator.
Yeah, I know. I know.
Yes, to AWS.
Yeah, in the lab we have ABS and AWR. Those that really like ABS, they could learn how to use it. I don't know really This is Mikko, the expert here. But we will try to do it using AWR because it's the most used in the lab. But also we have the possibility to run ABS in case of it.
So we're all invited tomorrow to start with the practical session. So we'll meet here at 3 p.m. tomorrow.
We promise not to be late. Sorry about that.
Tomorrow
We made it.
will be better.
Wait a
10
minute.
minutes. Oh, no, we did it fast.
Tomorrow we try to design something special or
Well, the idea of the whole session, it will take 2 days. It's a low noise amplifier based on the model of a one transistor that it was published and it's already on the Google Drive. So if you look at the PDF, it would be the model of one transistor that is there already, and it was used before for the design of 40 gigahertz element. So now we only take that transistor, and Mikko will teach the technique on how to design the environment so that transistor is turned into a stable low noise amplifier. It's awesome. Fantastic.
But I think this is really useful because it's a tool not only for microwave LNAs embedded, but also can be used for other kind of design. For this particularly focused on.
Cool. So thanks very much, guys, and we'll see you tomorrow. Thanks very much to Mikko and to continue tomorrow. I think we have to
Finalize?
finalize.
And see you guys.
Bye. See you.
No, I mean,
See you later, alligator.